Alright, starting off chapter 6 here. Chapter 6 has to do with, it's called rational exponents and roots. And this is another really type of function that we're going to deal with here. Where it comes from is the use of the Pythagorean theorem. A geometry student, boy, about 250 BC. Imagine that. They were solving stuff using the Pythagorean theorem. And so what he figured out, like, you know what, how about if we have a square, which is 1 inch across, 1 inch high. The question is, what is the diagonal? What's the length of the diagonal? And up until that point, people thought all we needed were counting numbers, whole numbers. We need the 0. We need integers, because some people have debt. And we need fractions. And that's it. So like the Egyptians, they never thought about square roots. They just thought about fractions, because you can do a lot of stuff with just fractions. So up until the time of the Greeks, we have this little issue. Is if I do this calculation using Pythagorean theorem, I get c squared, which is this. 1 squared plus 1 squared is still 2. And then the question is, what fraction makes this true? Because that's what got stuck. So you kind of think, okay, give me some numbers here. What fraction do you think, if I square it, gives me a 2? 1/2, cool, let's go with it. So take 1/2, we square that. Gives me 1/4, right? Because when you square a fraction, it actually goes down chunks. How about 3/2? Maybe 3/2 will do it. 3/2. Square that one, gives me 9/4. Hey, pretty close, huh? That's like 2 1/4. So then if I take, how about if I take 9/4, square that one? It's 81 over 16. I don't even know what that is. But it's still not 2. Right? And so that was the problem during the Greeks here. So we had to invent a whole new set of numbers to figure out the length of a diagonal across a square that's 1 inch in length. And so what we come up with is the whole concept of roots. So number 1, though, it says give the 2 square roots of 36. That's pretty easy. Yep, 6 and -6, right? But as soon as we do that, we're faced with another problem. Very big problem. And we have to go all the way back in our mind, all the way to chapter 2. You guys remember in chapter 2, we learned about functions. And in order to be a function, if I say a number, as a class, you should all say the answer to me. There should not be disagreements among us. So like a function like this, f(x) equals 2x, right? Everything gets doubled. That's a function. Because if I say 3, all you guys say 6, right? You just double it, right? Okay, if I say 12, you guys say 24. So if I say, what are the roots of 6? I'm sorry, roots of 36. There's 2 answers. There's a 6 and a -6. And so we got to figure out how we're going to do that so that we only get one answer. And so our fix-it problem is this. We're going to use this little weird shaped, almost looks like a division symbol with a little hook, which you've seen before. And technically the name of this, it means the positive square root of. That's what it means. Math teachers, totally lazy. We don't say positive square root of. We just say square root. But in your mind you should think, okay, it's only the positive answer, not the negative. So positive square root of 36 is 6. And the question always arises, Mr. H, how do you get the -6 then? If you really want the -6, you just put a negative in front of that symbol. It's called the radical symbol. Again, what it means is just a positive. So the positive square root of 36 is 6, with the negative hanging out in front, makes a -6. Cool. Any questions on that? That's the major concept here. Okay. So this one, there's the definition of it right here. It just means this right here. It's the positive number we square to get x. So I like that little definition in words right there. So is the positive number we square to get x. Okay, cool. Let's go with it. Is it only a square root? No, we can go on for higher and higher forever. The only thing is, if you don't see a little number over here, it's called an index. We would normally assume it's a 2, it's a square root. But yes, you can go higher. You can go third root or cube root, a fourth root, a fifth root, and you go on forever, forever, forever. Okay, so we have that. Alright, so let's try some. Few ones that you should know, probably a bunch have memorized, and I like this. I think this is the first algebra textbook I actually seen that actually put this in. Because normally with the textbooks, they just assume you know this from pre-algebra here. So, your square root functions, a lot of the common ones, the cube roots. So if you take a 2, you keep on multiplying times itself. 2 times 2 times 2 eventually becomes an 8. So again, cube root of 8 is 2. Cube root of 64, that's kind of funny. So 64 actually is a perfect cube, and 64 also is a perfect square. So it serves dual purposes. 1 is a perfect everything, right? 1's a perfect square, 1's a perfect cube. 16 is kind of funny. 16 is a perfect fourth root, also a perfect square. So kind of be mindful that you got to think of what you're doing. If you're just taking, you can't just say 16. It has to be a fourth root of 16 or a square root of 16. We'll give you different answers. Okay. And then we got this little problem too, which kind of arises. We might as well handle it right now. The whole concept of negative numbers. If I say this, answer for this guy, I need a number, I need a positive number, which if I square it, gives me negative 36. Is that possible? 6 times 6, but that gives me 36, not negative 36. So if you see a negative inside a square root, now we'll talk about higher roots in just a second here, but inside a square root, for online purposes, you're going to put DNE. For as far as paper pencil homework, you're going to say no real root. Now there is an answer to this. It's called the complex number system, which we'll get into a little bit later. Alright, but we should have in our minds this right here. So if it's you can't have even amount of positive numbers to give you a negative answer. It doesn't happen. But what happens if we go a little bit higher? What happens if we go cube root? Is this possible to have? Could I have a number cubed to give me a negative 27? Yeah, negative 3, huh? Because negative 3 times negative 3 is a 9, and still times another negative 3 makes the 27. So yes, negative, or we call these guys odd roots. Odd roots can actually handle negative numbers. Any even roots cannot handle any negative numbers. So let's keep that in our mind there as we do them. So odd roots can handle both positive and negatives. Even roots can only handle positive roots. That's it. Okay, so I think now we're ready to do some problems here. Alright, since we're covering 3 sections today, I'm going to go kind of a little bit more quickly than normal here. But you guys keep up if you like. Go ahead of me if you like. I'll sometimes tell you, try it yourself first here. It's like this one, try it yourself first real quick here. We'll correct it. Alright, the cube root of a negative 64. What number times itself 3 times gives you negative 64? Yeah, negative 4. Are we good? How about a square root of negative 25? Yeah, does not exist, or no real root. And again, the reason why this is no root, because we're in the real numbers. If you move on to different types of numbers, mostly used in electrical engineering, this does have an answer, because we need it to have answers with engineering. Okay, 4, 5, 6, all yours, go for it. Try it yourself real quickly here, and I'll... a negative square root of 4, is it possible? Absolutely, yeah, because the negative is on the outside of the radical, not inside. So square root of 4 is a 2, but then you have a little minus in front. Fifth root of negative 1, possible? Yeah, for odd roots it is, yeah, which is negative 1. Okay, fourth root of negative 16. Nah, not a negative 16, right? It's an even root. Even root cannot handle negative numbers. It is a DNE. So no real root. Alright, do a quick here, show of hands. How many got all 3 correct real quickly here, just so I know where we're at? Okay. About a little bit over 50%. Alright, now let's introduce variables into here. How do we work with variables? Number 7, number 8. So, one little thing it says on the homework, sometimes it says this, sometimes it doesn't. So we got to assume all variables represent non-negative numbers. We just figured out the problem is, right? If it was a negative 5 in here somewhere, negative 7, then square roots won't happen at all. So assume that the a and the b are just positive numbers. So how to deal with that? Well, we deal with them individually here. So 81, square root of 81? 9 is good. Now let's deal with exponents. A to the 4th. What squares to give you a to the 4th? A squared. Okay, this is the difficult one for some. What would square to give you b to the 8th? Let's go for it again. It goes off of your rules for exponents. Let's see. Let's go backwards to see how it works, because we looked at exponents in chapter 5, I believe. Let's see. If I were to square this, right, which is the reverse of square rooting something, there's your 81, or 9 squared, right? Each of these have to be squared. So a squared squared, b to the 4th squared. So there's your 81. There's your a to the 4th, and there's your b to the 8th. So whenever you're dealing with exponents and you're taking the square of them, square root of them, technically you're just dividing. So we take roots of numbers, but we divide exponents. Okay, cube root. That's okay. Let's go for it. I'll let you guys handle 8. Alright, and again, the cube root of 8. 2 is good, right? And the cube root of x cubed. Just to x. Again, think about division here. Since this is a cube root we're dividing by, we're dividing technically by 3 this time. So y to the 9th becomes y to the 3rd. Again, just sort of showing it again in terms of cubing something. The 3 goes to each one of those pieces. And there's your 8, there's your cube, and there's your 9. Alright, the next one, trying by yourself as well here, if you haven't done so already. Alright, hopefully got the hang of it by now here. Let's see, 4th root of 81 is 3. right? Because 3 times 3 is 9 times 3 is 27 times another 3 gives you 81. And again, it's division from here on out. So 4 divided by 4 is a 1 for the A's. 8 divided by 4 is a 2 for the B's. So B squared. Alright, next step here in the process here. So we learned about the roots. Now let's talk about rational exponents. Well, it means, what does it mean to have a fraction in the exponent? And so this is what the book says. This, I'm going to give you more of an abstract definition here, which will make sense a little bit later. I just wanted at least for you to see it right now. But notice if you have a fraction in the exponent, what really that means is the denominator becomes the root. So in the exponent, the denominator is the root. I like it like this because it kind of makes sense to everything. So x is the base. Whatever is the numerator, that is your power. That's what you're going to take powers of. Whatever's in the denominator, that is your root. That's what you take the root of. So if it's 8 to the exponent of 1/3, technically what it really means is it's the cube root of 8, which is 2. Okay, we good? So the next few examples, what they want you to do is to kind of get this concept across. You're going to go from one to the next and then simplify, because they want you to sort of build that understanding. So write this expression as a root first, and then simplify it, if it's possible. So 9 to the exponent of 1/2, what does that really mean? That really just means the square root of 9. And then we can simplify that down to 3. And of course, eventually you should be able to understand. You see 9 to the 1/2 exponent, you just say 3. But sort of building the connection here. Okay, so 27 to the exponent of 1/3, really what that means as a root is the cube root of 27, which is 3. Okay, and the problem that probably occurs the most often with students and exponents is the whole concept of parentheses. And so 12 and 13 deal with that. Let's do this one together. So if you do not see any parentheses here, that 1/2 is only acting on the 49. The negative just sort of sitting outside. If you do see parentheses, that 1/2 is acting on this whole entire thing. You need the parentheses in order to include the number. So in this case, the little negative is just sort of sitting outside. And we're taking the square root of 49. Okay, square root of 49 is 7, and then the negative in front makes a -7. Okay, going down here, now with the parentheses, that means the 1/2 is acting on the -49, which makes a square root of a -49. And answer to this one? Perfect, no real root. Again, online homework, you just put DNE. Oh. Alright, and then, I think it's from chapter 4. Chapter 4 that we did this? It is all the exponent rules. I just want to find out where we did this. What's that? rules from chapter 1. There they are, yep. It was in 1.2 and 1.5. So now we come back to this here. So again, if you multiply numbers with the same base, all we really have to do is add the exponents. If you take powers of powers, all you do is multiply the powers together, that gives the answer. If there's two types of terms here, and you're taking powers of, you got to take powers of each and every single term. Again, a negative exponent really means reciprocal. You take it down to the denominator. If you have a quotient taking powers of it, that power has to go to each of those here, to the numerator as well as denominator. And if you're dividing numbers, all you do is you subtract exponents. The one that didn't include, which they should have, this one here, is any number to the 0 power is 1. Okay, good. So let's start. Let's start with simplifying exponents using those rules. So 16 over 25. What I'll do here is I'll put the 16, the 1/2 exponent goes to here, 1/2 exponent goes to here. Alright, and if you need to still reduce this down to like a square root of 16, that's fine. If you can go directly down to a 4, that's fine too. So 25 to the exponent of 1/2 really is the square root of 25, but eventually you get 4 over 5. Okay, so 15 actually goes the other way. Since we know this rule now, can we go from here? We can go and put this into radical exponents. And we actually did this one before. This is number 8 from before, but we want to just kind of see it in a different way. On the homework, it actually won't tell you to do it this way here. Just say simplify. But here, just to get the connection here. Write this radical in exponential rational exponent form. So we're going to take this 3 here, we're going to bring it all the way over here, and we're going to place it as a 1/3 here, right? That comes in as a 1/3. Alright, and again, if we have multiple types of numbers inside here, that 1/3 has to go to each and every single number, so that it goes to 8 to the 1/3, x cubed to the 1/3, and y ninth to the 1/3. Okay, and simplifying that, you should know that's a 2. These 3's cancel off because it's 3 times a 1/3, so 3 is reduced down just to a 1, so that's x, and then 9 divided by 3 is a 3, so that gets you y to a 1/3. So again, just getting a different presentation from number 8, seeing how they're all connected. Okay, this one is the same thing as number 9, just in a different format. Can you go from radical notation to rational exponent notation? And then from there, simplify. Give you guys a minute, try yourself. Alright, and let me start it as well here. So that's going to be 81, a to the 4th, b to the 8th, now taken to the exponent of 1/4. And that 1/4 goes to each one here. Alright, that guy reduces down now to a 3. Again, the 4's cancel, leaving a to the 1 power now. 8 divided by 4 is a 2, so how about b squared? Okay, so now we can sort of make that abstract form now. Got a couple of people still writing here. I'll wait a little bit. Alright, so in its most abstract form, here it is. It's a to the m over n. So you can think about this here. Think about this one, you can think about taking the root first, then taking the power, or you can think about taking the power first, then taking the root. It doesn't matter which way you go, but to make it a whole bunch easier, we're going to do this one first. We're going to take the root first, then powers. Because if not, then you end up with humongous big numbers that you're going to take a root of. Like, nah, I don't think so. And this one kind of thought it was kind of cool. This one sort of proves it, that it can go either way. So this one proves the first, this one proves the second way here, and then proves the first way here. I just kind of include that in there. Because after you finish calculus as a math major, this is what you see from here on out. You don't see any numbers anymore. You just see letters. And you prove that algebra actually works with variables. Then you prove that geometry works with variables. Then you prove any kind of formula works with variables. And then you prove calculus works with variables. It's kind of interesting idea there. All right, but this whole concept here is what we said before. It's kind of like this. It's x to the p over r. Power is the top one, and r is the root. All right, let's go for it. So 17 and 18. 9 to the 3 halves exponent. Oof. Okay, let's do the root first. The root is 2. So technically this means what? Square root of 9? 3. I go with that. 3. And I personally like to put parentheses. Because with parentheses, that tells me exactly what I know, what I took the square root of, and what I got. So 21. Cool. Then again, the book says it doesn't matter which way you go, but if you take 9 to the third power, that's not going to be fun. Because it's going to be 9 times 9 is 81. 81 times 9 is 243. Then you're going to take the square root of 240. No. It's much easier to do it this way. Okay, so we'll go with it. 16, the fourth root of 16. Are we okay with 2? Right. A number multiplied itself 4 times to give you 16. Yeah, 2 times 2 is 4 times 2 is 8 times 2 is 16. Cool. And with that, no, actually 81 times 9 is 729. That's right, 729. And then you take a square root of 729. Not going to work. It's much easier to do the root first and then go from there. Alright, and now let's kind of put everything together. So exponent rules with this whole concept of fractions in the exponent. I'll do the first one, you guys try the second one by yourself. Here, let's go. A to the negative 2/3. First of all, negative exponent means what? It means reciprocal, is that right? So we're going to take the 8 down to the denominator. So 1 over 8 to the positive 2/3 this time. Alright, and then from here I think it's pretty easy. From here, then you look at, let's see, cube root of 8. 2. Alright, 2 times 2 times 2 is 8, and then 2 squared is a 1/4. There it is. Alright, 20, all yours. Alright, those are waiting for me. Let's go for it. So if you have already a fraction and you have a negative exponent, we just take the reciprocal. What's the reciprocal of 16/81? Means 81/16, right? Because it's a fraction already, you just change the numerator and denominator. And then remember, if you have a quotient here, remember the exponent goes to each and every single one, right? So the quotient has to go to the numerator, 81⁵, and denominator, so 16⁵. Okay, now let's deal with this here. Fourth root of 81. I go 3. Okay, and the fourth root of 16. 2 is good, yeah. So, and then we have 3 times 3 times 3 on top makes it 27. And on the bottom, 2 times 2 times 2 makes 8. Okay, good there. Alright, so now let's bring in the variables. Alright, so again, what do we do here? If we're multiplying numbers, what do we do with exponents? We have to add them, so it's really technically 1/2 plus 1/4. Then for these problems, you may want to have to do this off to the side, unless you can do it sort of quickly in your head. So off to the side, we have to add 1/2 plus 1/4. Common denominator would be a 4 at this point. So 1/2 makes actually 2/4. 1/4 stays the same. Adding together makes 3/4. Alright, give you guys 22 and 21. Sorry, 22 and 23. Try yourself. Again, think about the exponent rules. Alright, I'm going to try it as well here. So if you have an exponent inside a parenthesis, exponent outside, what do we do with the exponents? Good, we multiply them, alright. And you may want to do this off to the side here. It says 3/5 multiplied 5/6. In this case, hey, the 5 is reduced, don't they? Actually, the 3 and the 6 also reduce, right? How about that goes away, that goes away? Just with the 2 on the bottom. So all this actually now becomes y to the 1/2. And I've simplified it. Okay. Again, what do we do with exponents if we're dividing numbers? Subtract. So z to the 3/4 subtract 2/3. And again, this one, if you want to, you can do it off to the side and then just put your answer down. That's kind of what I did. No point of writing that z over and over again until I'm good with it here. So let's see, for the common denominator would be 12. So 12. 4 times 3. 4 times 3 gives you 12, so 3 times 3 gives you 9. And then 3 times 4 gives you 12, so 4 times 2 is 8. Common denominator is 12, but if you subtract 9, or 9 minus 8 would be a 1. Perfect. There it is. There is my simplest form. So z to the 1/12th. Which kind of, if you think about it, kind of interesting. It's the 12th root of z. Cool. All right. Number 24, 25, last ones. They're pretty difficult. I'll let you guys try it. Try it yourself first. Give you maybe half a minute or up to a minute here each. Try see if you guys can handle that one all by yourself. I'm going to try it here. So yours may work out a little bit different from mine, but we still should get the same answer. Good. And if you're not quite sure if you did it correctly, come talk to me after class and say, Mr. This is what I got. That's correct. Okay. So first things first, I'm going to take a look at this little negative exponent here. And with that, I think I'm going to take it down to the denominator first here. But you could have, if you wanted to, you could have actually multiplied the 8 into each of this one and this one. That's fine too. So with these 5 or 6 different ways to do this correctly. I'm going to just pick one of them here. So because the negative exponent, I'm going to take the a down to the denominator. So 1 over a to the 1/4. Sorry, b to the 1/4. Sorry, a to the 1/2. And then we're going to take that to the 8th power. All right. So 1 to the 8th power. Just 1. B to the 1/4 times 8. Here we go with 2. That's kind of really just 8 divided by 4. This one is going to give me a to the 4. And the only thing I don't like about this here, even though this is correct, the only thing I don't like is the fact I like my variables in alphabetical order. So I move the a out in front of the b, so 1 over a to the 4th b squared. Okay. Even if you did a different way, raise your hand if you got that answer before I showed it to you. Cool, okay. Raise your hand if you did it a completely different way than me. Still got to that answer. Okay. Yeah, another way to do it is to multiply that 8 into each of these pieces here. So that would be a negative 4 here. This would be a positive 2. Let's actually try it. Let me show it to you how that works. So that would be this to the 8th. That would give you a to the negative 4. That would give you b to the 2nd. And then notice what we're going to do with that a. We're going down to the bottom here. Put it in front. And there it is. Still the same thing. See again? Okay, cool. That's by popular method there. Yep. Okay, 25. Ooh, you know what? Let's try this one together. Unless you want to go ahead of me. Give you maybe like 20 seconds to go ahead of me if you like. Otherwise, we'll do it together. me start it. So I personally like to get rid of negatives right away. So that's just kind of me here. So what I'm going to do, I'm going to leave the x to the third over here. I'm going to make a fraction out of this because that y has to go to the denominator. But the only thing is, see this little 6? I can't take this y over here because that will take it out of this. So it's going to be y to the 3 over all that in terms of 6. And then this is all the way in the bottom here. X fourth, y 10th. Okay, now let's deal with this here. So 6 is going in, but I got a 1/3. So that's going to be x to the square is good. And careful, you do have complex fractions here, right? There's a fraction on top here. So then I got this one, y to the 18 is perfect. And this stays the same. So this is x fourth, y 10th. Oh, I think we've seen this before, didn't we? Last chapter. We're going to put a little 1 underneath all that. Then we're going to change this into a multiplication problem instead of a division problem here. So the top remains the same. It's x squared over y to the 18th. And we just take the reciprocal of this guy. So now it's going to be multiplication of 1 on top, x to the 4th, y to the 10th. And can you simplify that down further? Let's see, the x's cancel, so it leaves you with a 1 on top, but an x squared on the bottom. Hey, just left with 1's on top. So 1 on top, and let's see, I put alphabetical order. So x squared goes first. Y to the 18th times y to the 10th makes y to the 28th. Remember that we add exponents anyways. Different way. You put in the 6 first. Alright, we good? Alright, that's 25. Sheesh, 25 problems for one section. That is the longest section. Sections will get shorter and shorter as we go. So now we're going to talk about simplification. What it means to simplify these radicals. And then we're going to talk about multiplication and division, because those are all tied together. Simplifying, multiplying, dividing. 6.3, then we're talking about adding, subtracting after that. So, property of radicals. This is one right here. This is called the multiplication property. It just says this. If I have two things that are multiplying inside the radical, I can think about them as two different radicals multiplying each other. And it also works backwards. If you have two radicals multiplying each other, I can put them underneath the same radical and just multiply the terms together. Again, there's a little proof for it. Let's give us an example of it though. So if I have a square root of 2 multiplying a square root of 3, I could just think about it as a square root of 6. We good? But going backwards, because this is where the power of it here. If I go like this, and if I say this is a square root of, think of a good number here. Let's go 10. Think of this as a 10. I could think of this as a multiplication between a square root of 2 and a square root of 5. Good there? So it kind of works back to them. Multiplying together, I can break them apart. Alright, then we got the division rule for radicals. Here it is. If I have a quotient that's actually inside the radical, I can split apart into two different pieces. And again, two different pieces I can put back together again by that. Let's see what would be a good one here. 3/4 would be kind of good like this. There it is. There's a fraction here inside the radical. I have the ability, because of the quotient rule, to break those up like this. Going the other way, if I have a square root of 50 over square root of 2, I can put those together. Okay, that's kind of cool because you know what, that actually will simplify, huh? That would be 50 divided by 2, then I can keep on going with the simplification of it. So that's what it's there, so it can simplify. Okay, so let's go for it here. So write square root of 18 in simplified form. We want to simplify this as much as we can. The way we're going to do it, it's called the algebra method of doing it. And then I'll show you the pre-algebra method, which I think you'll like, oh yeah, I remember that. So square root of 18, what we do is we think about this here, because you guys are sophisticated Math 63 students. I want the biggest square root that is a factor of 18. Yeah, 9. 9 times 2, right? 9 is the perfect square. So I can write it like this. Square root of 18 technically is square root of 9 times 2. And we got this multiplication rule that says I can split this off into two different pieces. I can split it off as a square root of 9 and square root of 2. And then square root of 9 technically is just 3. So how about 3 root 2? Good there. Alright, remember this was the pre-algebra way of doing it. You took the 18, and remember breaking it down into different pieces with the factor tree? And you break that into 3 different pieces until you get all prime numbers. And remember how we used to collect doubles, right, for square roots. We used to collect triples for cube roots. Right? But this time, I think we know we can figure out the 9 that's there. So most of the time we can do that. If you really, really get stuck, you can go down to this level. But most of the time we'll figure out what the perfect square is there. Okay, 2 is all yours. And then you might get stuck with the exponents, but we'll see how that works. Alright, so let's go for it here. Again, perfect square, which we're looking at. So 50 is 25 times 2. So 25 there. We'll leave the 2 over here in a little bit. X squared. That is a perfect square, isn't it? And so if you think about perfect squares, we're thinking about second power, fourth power, sixth power, eighth power, anything that has doubles of their power. So y to the third, the perfect square, that is just y squared. So then we have some extras. What's the extras? Yeah, 2 to make the 50, right? 25 times 2 makes the 50. X squared is already there. We need an extra y over here. Remember, because when we multiply numbers, we add exponents. Split them off 2 different pieces here. So 25x squared, y squared on one side, and 2y on the other. And eventually that becomes a 5. That's just an x. And that's just a y. And then we got the leftovers over there. Okay, the only thing you got to be careful of that I see students do a mistake here, this little radical symbol, this little extension right here, just make sure it's not just over the 2 but over the 2y. Make sure it finishes off the number, the last number that you have over here, because that is always an issue there. Cool. Alright, 3 and 4, very similar. Careful, this is a cube root. So then you're thinking about perfect cubes now. And if you want to, in your mind, just sort of start cubing numbers here. 1 times 1 times 1. 2 times 2 times 2. 3 times 3 times 3. 4 times 4 times 4. See what those numbers are. Alright, I'm going to start it here as well with 30. 54. So now in mine, this is what I do. So 1 times 1 times 1 is 1. That's not going to do it. 2 times 2 times 2 is 8. So 8 times... That's not works. 3 times 3 is 9 times 3 is 27. 27 times what? Yep, that's 27. Because 27 will be the perfect cube that multiplies to give me 54 by 2. Because 27 times 2 is 54. Alright, a to the 4th. Remember, we're looking for perfect cubes now. So we're looking at multiples of 3, right? So 3, 6, 9, 12 is exponents. So a to the 4th really is a to the 3rd and then the extra. B to the 3rd is there, all of it. So again, the leftovers, I got to extend this out a little bit here just to put in all the rest of it. Let's see, 2. Yeah, 27 times 2 gives me 54, and then I need an extra a in here. The extra a is going to do me. Alright, splitting them off here. And you know what? You don't have to split them off. If you can go directly to the answer right at this point, you're good, because you already know what that is, right? You already know that side. So 27, cube root of 27 is 3. Cube root of a cubed is a. That's going to be b, and the leftovers are 2a. Don't forget, the little thing that students always forget as well here is right here. That little 3 still has to be there. If you're taking a cube root, you're still taking the cube root of 2a. Because if you don't put that in, that just changes it into a square root now. So careful there. Ha! See what some of you guys put in the 3. Okay. Okay, and 4, let's see, 75. Perfect. 25 and 3 would do it. Okay, since we're talking about square root, we're talking about even powers. So that'd be x to the 4th, with an extra x coming in later. Y to the 8th, that's all good there. Times 3 this time, is that right? 25 times 3 gives you the 75, and I need an extra x in here. That could give me x to the 5th. Because I think once you split it off into this, you're good. You know what the answer should be then at that point. That's a 5 coming in. Let's see, that's x to the 4th, but we're taking the square root here. So everybody okay with x squared? Okay, again, it's the division, right? It's dividing by 2. 8 divided by 2, that means you have y to the 4th still. And the leftovers would be 3x. Alright, number 5 you can probably still do by yourself. Go for it. Number 6, wait on that just for a little bit. We'll do that together because that goes into the quotient rule now. as well. Okay, perfect fourth root. Okay, so let's talk about this here. So 1 times 1 times 1 times 1. I do that more 4 times, right? So 2 times 2 times 2 times 2. 16. Is that a multiplier of 48? And let me try another one here. 3 times 3 is 9 times 3 is 27. Times 3 again is 81. 81 is way too high already. So if the only one I'm probably going to try is 8. That's 16. 16 times 3, I go with that. 16, don't forget the little 4 on the outside, the index here. 16 times 3 again. So now we're looking at multiples of 4. So a to the 8th is good. B to the 5th, so now we're going to reduce it down to b to the 4th. That would be good enough there. C to the 4th. So what are my leftovers? (16 times 3), is that right? That gets me the 48. And a to the 8th I got. B to the 4th was b to the 5th, so I need another b over here. And C is okay. Whew, so final answer. Don't forget it's a fourth root, so that means it's going to be a 2. And again, these are all divisors now. So 8 divided by 4, 2. 4 divided by 4. 4 divided by 4 again. And the leftover. Cool, alright. Let's move on to the quotient rule here as we start. So one thing, whenever you simplify stuff, you can't have any fractions inside the square root, or any kind of root. That would not be considered simplified. And so what we do is we split it, just like the quotient rule says. I can take this 5, square root of 5, leave it by itself, and take the square root of 9, leave it by itself. Okay, the other thing that shouldn't happen is you should not have a radical in your denominator. That's technically not considered square root, even though sometimes we allow it to happen. So in this case, the square root of 5 doesn't reduce, but the square root of 9 does perfectly. So it becomes a 3. Now that would be a simple form. Only thing to check for is just to make sure, since we split it, make sure 5 doesn't have a perfect square inside it. So if this was 16 or this was 50, then we would simplify that a little further. Okay, so let's go one step further. That was an easy one, so we don't spend much time on that. Because number 7 works the same way, except there's a little problem. Because if you split it, root 2 goes on top, root 3 goes on the bottom, and that root 3 doesn't reduce very nicely. That is weird. Okay, so I think you guys know for Math 61, what do we have to multiply by? Yeah, let's stop there just for a little bit here, though. I'll leave that as a suspense here. Let's go over here. What? We're trying to figure out this. We're trying to multiply by something so that I can still keep an equal sign. I'm going to multiply by something so I can still keep this as the same. Okay? So let's come over here just real quick here. I know we did this in chapter 1. Just kind of make you think through it here. See if you guys agree. Is this the same thing? Yeah, 3/4 technically is the same thing as 6/8. How come? Cool, okay. Let's leave that alone just for now. Are those the same thing? Yeah. The reason why 5 is the same thing as 5 is because I get to multiply by 1 and they're still the same. Right? If I can reduce something down to a multiplication of 1, I've done it. I've got the same thing and keep my equal sign. And these two numbers are the same. So what is the 1? So is this true? Is that true? And everybody should be shaking their head. Mr. H, yes, that is absolutely true, Mr. H. Yeah, because 1 could be anything you like as long as the number on top and the bottom are the same, so technically this is. And that's what makes it true, because they're technically still multiplying by 1. But that 1 could be anything, right? In this case, what we want is we want to keep it as a square root of 3 and a square root of 3. The reason why we want the square root of 3 is because we want a perfect square over here. Just like number 6, the last problem, I want this guy to be a perfect square. So on top, That's easy. Got a square root of 6. On the bottom, I technically have a square root of 9, but let's not do that because we have to rewrite the whole entire problem because I just put 3. Okay, but real quickly here, careful here, because with number 9 it's going to change a little bit. The reason why I'm doing this is to get myself a perfect square. If this was cubes, then I would have to get myself a perfect cube. If it was fourth roots, I get myself a perfect fourth power number. We good? So kind of careful there. That you didn't see in Math 61. Okay, this one, it's called rationalize the denominator. Exactly, because that little radical 2 is there. What should I multiply top and bottom by? Square root of 2 would do it. Alright, what do I have on top? Yeah, let me erase this other stuff here. On the bottom, just a 2. The only thing we also have to think about, just maybe the 5 and the 2 will reduce. Now because the 2 is an outside number now, those could reduce somehow sometime. Alright, and then the other thing that comes up here, notice when you multiply these, notice the 5 is an outside number, the square root of 2 is an inside number. When you multiply them, you just sort of put them together. That's a question that comes up. How come the 5 and how come it didn't become the square root of 10? The reason is because of this right here. If you have a 5 by itself, technically what you have is you have a 5 root 1. If you have a square root by yourself, what you technically have is a 1 root 2. And what happens is outside numbers always multiply outside numbers. That's a 5. And inside numbers always multiply inside numbers. Good there? Let's see. No, number 9 is not the change. Number 10 is the weird one here. Okay, let's put in variables. Number 9. What should we multiply by in order to get a perfect square of 2y? Yeah, square root of 2y and both top and bottom. Alright, let you guys finish that one off. And then number 10, try it. Go ahead, try yourself, see what happens with that. Alright. Hopefully you guys finished it off. Here's the 3 is the outside number. The square root, actually that's a multiplication, so that'd be 10xy. On the bottom, I just have a 2y. And again, does the 2 and the 3 reduce? Yes or no? Also, since you multiply these two together, it could be possible that this now is a perfect square. So kind of careful there. If it was like maybe like a 3 here and a 3 here, now you got a square root of 9. So kind of careful there. You may have to do a little bit more work there on the homework. Okay, number 10. Notice okay, you haven't seen this in Math 61. So notice you have a cube root of 9. So the question is, what should I multiply by in order to give me a perfect cube? Not a perfect square. So notice I have 9 is really made up of 3 times 3, right? So what I technically just need is I need an extra 3 to do it. So that's what I need. So that means that will make a 27, and the cube root of 27 is 3. So careful. It's not always just multiplying by the same thing you have in the denominator. It's forming that perfect square, perfect cube. And yes, that's the reason why I made you do it, so you can start erasing. So then you can say, oh, shucks, that's right. Okay, 5 is the outside number, so 5 on top, cube root of 3. On the bottom, I just have a, well, let me show it to you, it's just so you see it. Cube root of 9 times 3 is 27, and that is going to be just a 3. And again, see if 5 and 3 reduce. Alright, number 11. Let's see, this is the sort of as difficult as it gets right here. So if you're still getting this one and your brain is intact and not hurting too much, you're doing good. Alright, so first things first, let's go to this one together here. You got to check whether you can reduce top to bottom. So if this was a 49, before you do anything else, you'd reduce this down to a 7. So see if you can reduce the fraction. If you can't, then you got to split it off like we were doing before. So everything in the numerator goes underneath a single root, and everything in your denominator goes underneath a single root. After we do that, then the question arises again. Is there any perfect square within each of those roots? Let's take a look at the top again. Hey, 48. Yeah, hold on. 48, yeah, we did 16 times 3 last time, right? 48 is 16 times 3. Okay, and square root of 16 is 4, so I get a 4 on the outside. Let's see what happens with the x's here. I got x to the third. We got 1 and 1 left over, right? So let's keep the leftover part just a second here. It's a y to the fourth. Divide gives me y squared. Okay, and the square root of, let's see what's left over. 3, yep, 3x. Okay, on the bottom, does that reduce any? I don't think so, no. 7z is not going to reduce. Still stays 7z. So the next step is just simplify if you can. Once you got to this step, now let's take a look at getting that rid of that 7z radical. So multiply both sides by radical 7z. And hopefully finished already here. Let's see what happens here. On top, there's a 4xy squared. Multiplying these guys together makes a 21xz. On the bottom just becomes a 7z. So a few things to think about first of all. Can I now reduce anything over here, the outside numbers? Right, no outside numbers reduce. Second thing is, did I form any perfect squares now inside here? Nah, 21 is still made of 3 and 7, right? And there's no squares now because of that anyway, so okay, good. Okay, one thing we still have to do. So let's take one more abstract concept here. So far we've been dealing with the variables being always positive, right? Assume they're positive, assume they're positive. So now let's talk about what happens if they're negative. The reason why we assume variables are positive, because many times in word problems in real life situations, our variables are positive. If you're looking at the number of seconds in a certain situation, right? You're not going to look at negative seconds. I mean, so a lot of situations you don't even look at negative ideas here. If you're raising, let's see, raising chickens and hogs in order to sell at the market, there's no such thing as -3 chickens. So, but sometimes we do have to think about the negative concepts here. So let's take a look at this here. Two examples here, and we'll make some deductions here. So if I take 3 and I square it, it becomes 9, and then I take the square root of it, notice it becomes 3. So if I square something and I take the square root of that something, I get the same thing back. That's kind of cool. Now let's take a look at the case, what happens if it's a negative. Let's see if it's a -3. If I take a -3 and I square it, hey, the negative went away, right? Take a square root of that, it becomes a +3. So here's what I'm going to do. I want to be able to do this very quickly. If I see this, I want to be able to get to here. See this, get to here. And so notice it's the same exact number, right? The one thing that has changed is change the sign. So, what operation did you know of in math that if something is positive, it stays positive? If something is negative, it makes it positive? Absolute value, right? Doesn't absolute value do that? So instead of doing this problem, if you see something being squared and taking the square root of it, all you really got to do is take the absolute value of it and you're done. So that's what this says. If you square something and take the square root of something, the easy calculation is just take the absolute value of that something. Now that works for even roots. Let's look at an odd root. What happens if it's odd roots? And let me do a positive. Let me do a positive 2 here first before we get to -2. So let's go over here. And so if it's a +2, that's easy, right? 2 times 2 times 2 is 8, and the cube root of 8 is a 2. So if it's positive, stays positive. 5 cubed makes cube root of 125, and the cube root of 125 is still 5. So positive stays positive. But with an odd root, if you take an odd number of negatives, you still have a negative. If you take the root of a negative number, you still have a negative. So that's weird. So for odd roots, you don't need the absolute value because it's always going to be that same number all the time. For even roots, yes, you need the absolute value because that's going to provide you with the correct answer from what we saw. Okay, so let's go for it here. 5, 6 problems having to do with this issue here. So again, on the homework, you'll say, do not assume variables are positive numbers. Alright, so let's go for it here. So first, numbers themselves are pretty easy. Square root of 16 is 4. No need to do anything there. But the square root of x squared, do we need absolute values? Yeah, for even powers and even roots, yes, we need absolute value. So for this one, let's say the x was -7. I don't want to put in a -7. Squared makes 49. 49 times 16. And then take the square root of that humongous number. It's a lot easier for me to go here. -7 in here, absolute value of -7 is 7. 7 times 7, 7 times 4 is 28, and I'm done. Whole bunch of easier calculation there. Okay. Careful here. It's still a square root. Even though they're taking an odd power, it's still a square root. So let's make this into perfect squares first. So square root of 25x cubed, isn't that 25 times x squared times x? Good there? See if that makes sense. Alright, and then from here, just this part right here, just the beginning part, that's square root of 25 is a 5. Do we need the square root here? I'm sorry, do we need the absolute value here? Absolutely. And then we still also have a leftover. The leftover is this little extra x right here. So it looks kind of weird at first. That was like a slow sneeze here. Okay, so what does that help us with? It helps us with trinomials as well. So square root of x squared plus 10x plus 25. Isn't this a perfect square trinomial though? That is actually x plus 5 squared. So again, instead of doing all that calculation, do we need the absolute value? Way easier calculation now, right? I'm just going to take the absolute value of that plus 5, done. Or add 5, then take the absolute value of it. So it really simplifies algebraic expressions. That's a good thing. Okay, try 15 by yourself. See what you think can factor out. And once you have it factored out, see what else you can get it to. Alright, I'm going to try it as well here. So first of all, what gets factored out? What do they have in common? Maria? X squared is good? X squared. Leftovers would be 2x plus 7. Is that right? Again, still inside the radical. But at least I got factored it out. Alright, do we need the square? Do we need the absolute value? Absolutely. For the x squared. And the rest still stays inside the radical. Can't go out because it's not a perfect square of anything. So stays. Alright, and the last two here, pretty easy. Has to do with the odd powers here. So with odd powers, do we need absolute value? No. Whatever this number is, it is that number. So if you got a negative 3 there, stays negative 3. As long as you're taking the exact same root as the power and it's odd. So 17, answer is? You could do the work if you like. I mean, if you can, if you like. You want to do negative 3 times negative 3 is 9, times negative 3 is negative 27. The cube root of negative 27 becomes negative 3 again. But why do that if you could just write down the answer? Okay, last section. I got 5 problems to do. Wow, we did 3 sections today. That's crazy. But Thursday we'll do only 2 sections, so that's kind of good. Next Tuesday only 1 section, so at least going down. Alright, so all the way from chapter 1. Remember how we were talking about combining like terms? Well, the same idea applies to radicals, except we call them similar radicals or like radicals. So this is from your textbook here. In order to be a similar radical, it has to have the same index right here. So if you're talking about cube roots, they better both be cube roots, and then they also have to have the same number inside. So 2 different ways it fails. You can have a 5 inside there, but one is a 4th root, one's a 3rd root. So nah, that's not going to work because they have to have the same index. The other way it fails, you could have the same index, but the numbers inside the radical are different. So 8 and 9, nah, they're not the same anymore. So let's go to it. that's sort of the concept there. And let's do it one by piece. So first of all, do we have like radicals? Absolutely. So let's go from left to right. Let's actually go this way here. So I got 3 radical 5s, and I'm going to subtract 2 radical 5s. How many do I have left now? Got 1 radical 5. We really don't write the 1 down. Think of it almost like x's. So you got 3x minus 2x gives you 1x. So you have radical 5 plus 4 more radical 5s. How many do you have now? You have 5 radical 5s. Again, x plus 4x, 5x. Same concept, same thing. Okay, so 4 radical 50 plus... Ooh, these are not like the same at all. One's 50, one's 8. But hold on, though. Isn't 50... Doesn't it have a perfect square inside it? Yeah, 25 times 2. So how about this? 4 stays. That's going to be square root of 25 times 2, which really is... Square root of 25 is 5, right? So let's do it like this. Let's write it out in outside of the radical. Leftovers was how much? 2. Because remember, it's going to be a multiply between the 4 and the 5. It's always a multiplication. Alright, 3 radical 8. Let's see, 3 is on the outside. Is there a perfect square within 8? 4. And the square root of 4 is 2, so 2 goes on the outside. 2 left over inside. Ooh, so sometimes they actually can become like terms. So 4 times 5 is 20. 6 times, let's say it's 3 times 2 is 6. And add it together finally. Now we can add them together. Hey, that's a lot simpler version of that one over there. Dunk dunk. Okay, now let's deal with variables here. And notice, again, it comes back to this. Assume that x and y are both positive. So you have to deal with absolute value stuff. So give you guys, just try it here. Try 3 and 4 by yourself here. Give you guys maybe 2 minutes or so. And of course, both of them are going to work out just nicely because they're textbook problems. Alright, let me put up the answers here, see if you guys agree. And then, again, ask me any questions, any part of it. Like, Mr. H, how'd you get the 3x over there? How'd the 5, blah, blah. Go for it if you don't understand. with cube roots, so cube root of 27. It's 3, because 3 times 3 is 9, times 3 is 27. So it's a cube root of 27. Bless you. So a squared doesn't have a cube in it, because you can't divide out the 3. B to the 4th does finally, so you get 1b with 1 left over. Alright, good there? Maybe? No, not good. Brain is already fried. Mr. H, it's sputtering. Cool. And the last one has to do with fractions, of course. What happens if we're adding these guys together and they have fractions? So fractions with radicals. Let's see, square root of 5 over 3 and 1 over square root of 5. I guess the first question is, what is the common denominator? Remember, 3 is an outside number, right? Square root of 5 is an inside number. So common denominator would be, you need the 3 from here, you need the square root of 5, because those are different multipliers, right? If it was, if it was inside, if the 3 was inside the radical, if it was square root of 3, then yes, it would be square root of 15. Okay, so again, factor of 3, factor of square root of 5. Okay, so then again, what's the multiplier that multiplies 3 to give you 3 times radical 5? Obviously radical 5, so let's multiply radical 5 on top, which would be square root of 25, which actually technically is just 5. We good? So going back over here, what multiplies radical 5 to give me 3 radical 5? 3, so 3 times 1 is a 3. And then from here, yes, perfect. You can now add them up. Again, don't forget, this is a common denominator, so this is still a 3 radical 5, but 5 plus 3 is 8. Okay, the only thing that could happen here is that this turns out to be like 12 or something. So then 12 and then 3, those would reduce down some more. So kind of careful with that one at the end. Alright, we're good there? And that's enough headache for today. Oh no, maybe not. Let's see. Don't we have a square root of 5 on the bottom? That is not simplified. Gotta multiply through by just when you thought it was all done. So multiplying that out again on top, 8 is an outside number, 5 is an inside number, so just be 8 radical 5. On the bottom, anybody with an answer? 15 is perfect, yep. You get a 5 from these guys, and don't forget you still multiply by 3, so that's 5 times 3, or 15. Now we're done.